Our last talk for today, you've already heard from Chris. You're going to hear more about what they're doing at ESnet. I was personally super excited to hear about ESnet showing up here at NAF, and I didn't know Chris before this, but I'm glad I know him now, and we're going to talk more. Take it away.
Thank you very much. Yeah, I apologize in advance. You have to hear from me so much.
You already have the thing?
Yeah, I think we're good.
There you go.
Yeah, this is my dongle thing. USB-C is a nightmare. Yeah, sorry you got to hear from me multiple times. My excellent coworker Alex Ray was going to be giving this, but unfortunately he couldn't make it today. So you get to hear from me. Thanks again, Chris, for having me, and everyone. Really appreciate the opportunity. Today I want to talk about basically a real-world approach that we've taken to intent-based networking and service orchestration. I get paid by the buzzword, so figured I'd cram as many as I could in there. Yeah, I'm Chris Cummings, full-stack network automation software engineer. I also get paid by the buzzword in my title. At the Energy Sciences Network, like I mentioned earlier, part of Lawrence Berkeley National Lab, U.S. Department of Energy. Yeah, we do big science. Just a little overview of what we're going to talk about. I'll just kind of tell you what ESnet is and RNE networks. I'm not trying to sell anything because I can't, but I think it's useful context for why orchestration is important to us. I want to talk about kind of the concepts behind intent-based networking and orchestration, just show you in practice how it works for us, talk about the stack of software that we use to make that happen, and then I'll actually do a blood sacrifice to the live demo gods. And Scott, did you get the goat that I requested? Okay, well, we'll have to make do. Yeah, we have one in the back. Oh, well, okay, we'll make do. Yeah, so ESnet. Basically, it's a big service provider style network, mostly in the US. We are contemporaries to Carl Newell, who you heard earlier. Don't listen to him. Don't believe anything he says. He's a liar. But we're contemporaries with them at Internet 2. Basically, we run this large service provider style network that connects all of the Department of Energy's interests in high energy particle physics. So basically, if there's a big science research facility, we're moving, multiple 400 gigabit links of data, towards these institutions, and operating at this kind of high-speed scale with a large sprawling network really does matter quite a bit for orchestration. And I'll talk a little bit about how I think consistency is a big part of why orchestration matters. But consistency of configuration is really big to us because these science flows and all of this data is really important to the world, and there's a lot of money being invested in this by the government. And so as, good stewards of, the tax dollars that we all, as US citizens pay, we want to make sure that we are doing the best we can to make sure that science can move at the speed of ESnet or light, something like that. So I've said the term RNE. What is that? RNE is a research and education network. So like I said, Internet 2 is one of them. They're a colleague of ours. They're a peer of ours. ESnet's one of them. But if you think about this as a map of the Internet, right? Over here you might have, content providers, service providers, ISPs, all of these various types of networks that sit on this big mess of goo we call the Internet, right? But you also have, car company, insurance companies, and things like that. Well, there's this kind of bubble over here of research and education networks. So Internet 2, ESnet, our European colleagues, Géant, and then there's regional networks that operate within a state to provide connectivity to publicly funded institutions. There's a lot of these, and they all connect to each other, but they have slightly different needs than all of these folks over here, the Googles, the ISPs, the AT&Ts, et cetera. One thing I like to kind of showcase is think about the Dallas High Five exchange shown there, right? Very functional part of urban planning that gets cars from A to B, except in really high traffic times. But it's very general purpose. You can move quite a bit of cars point to point, and you can kind of go wherever you want. But it's going to be relatively slow. It's going to get congested at times. And if you tried to drive a really big thing down there, it's going to be real difficult, right? So they're general purpose, but they're not necessarily great for purpose-built stuff like what we try to operate, which is like the Shinkansen here, which is, a high-speed train that goes A to B as fast as it can, moving as many things as it can all at once. If you tried to take that on the high five, it's not going to be good. But if you try to take our science flows across the internet, it's not going to be good for the internet or for the flows. So we're trying to operate like a purpose-built network. So consistency is really important for that. All right. enough about us. Intent-based networking. So what is it? It's basically a high-level definition of a service that you're trying to offer. Here I do say network service, but I do think it expands past networking. But since we're all networkers, I think it's important to think about it in that context. So you're describing a service, but not necessarily how to implement it. So you're describing a thing you're going to offer, a thing you're going to sell, a thing you're going to produce, but not necessarily how you do that. That's the intent of intent-based networking. And essentially what you're doing is you're abstracting all of the service offerings that you have from the actual implementation details of how to make that go, how to make packets and bits and modulation happen on wires and things like that. Also, it's a buzzword, so I can make it mean whatever I want, which is also really nice. Orchestration. Also, I'm making up my own definitions here, but here we're coordinating multiple computer and network systems at the same time, right? So it's not just generating a bit of config and you're done. You know, you're talking perhaps to an IP address manager to reserve blocks, and then you're pulling that into one system, and then you're updating your DNS from that, and then you're using that to configure a backbone link between routers, and then you apply that config, and then you update a weather map that shows your traffic data, et cetera, right? You're talking to a bunch of systems, and it's point to multi-point, you know, octopus of config. The orchestration part of this really is what sits in between everything and translates network intent, so this, you know, idea of a service, into configuration, which is actually what makes it go. For us, it's a workflow-based method for provisioning services. So I'll talk about a tool we use called Workflow Orchestrator. It's open source, free. You can download it. It's a collaboration between us and another European inrun named Surf. And some other folks are also involved in it as well. But you know, the idea being you're taking a workflow of steps, you're taking these automations and you're compiling them into a list of things that need to happen to actually make a thing go. But yeah, as I mentioned, it's a method for actually ensuring that the services we deliver are consistent, right? Because ultimately we have to make sure that, you know, science data is flowing and that it's always able to happen. Because if we screw up, and, you know, Bob, who's really into configuring things his way, configures it the wrong way, then a lot of really expensive multi-billion-dollar facilities aren't able to basically be used for what they were built for. So with orchestration, it's always happening the same way. I think we can all relate to, like, and I've heard it even alluded to and mentioned a few times here, you know, oh, well, if you want to configure that, you need to talk to so-and-so. You know, he really knows how that works. And we've also all probably walked into a router. They're like, you look at that layer 2 config, you're like, oh, did Bob do that? This is a Bob config. You know, when the orchestration tooling goes out and does that, you don't go, who did this? Who did that? It's a computer doing it. It's doing it exactly the same way every time. It's very consistent, and you just don't have to worry about those kind of problems. But it's not everything, right? What isn't it? What is orchestration not? For us, it's not a replacement for network engineers. We actually have increased the number of network engineers we have. And I would say what it does is it expands the role of a network engineer so that they can actually focus on engineering and not just deployment of config. You know, the thing I'll demonstrate later is how to configure essentially a backbone link between routers. When I first started ESnet, we had not orchestrated that yet. And it was, I was tasked with spinning up 4 100 gig links in a ring, in our European network ring to expand some capacity. And just going through and figuring out, okay, what all config is required to spin up a backbone link? Who do I talk to allocate IP addresses? And figuring out the business process for something we hadn't done in a while was really difficult, and it ended up taking a week to get the configuration all done and approved and through change management. Now it takes 30 seconds, you know? So as an engineer, I was focusing on a lot of minute details. Now I can focus on how can I create something that better serves science and makes, you know, our organization better and actually enables us to do more cool things versus being stuck in repetitive tasks. It's also not a way to have necessarily one network engineer do the job of multiple engineers. You know, I really think that if you have people doing the kind of work that, like if you're just doing the work that anybody can replace, but just like swap off some person off the street to do it, like that's not really the interesting work that you should be working on as an engineer, right? So we're not trying to basically have someone just do a lot of work faster with this. We're trying to make it way more consistent and way more precise. And also for us, it's not the only tool that exists to run our network. We do have other tools. It's not an NMS. It's not necessarily the monitoring system or things like that. So I've kind of talked about some of these. The benefits are that it forces you to design and plan your services first, right? What you want to actually offer or do, not config. Config is a part of it, and you of course need network config. And usually we end up asking our network engineers, well, what does a config look like for this thing you're trying to do? But ultimately what we're trying to do is force folks to think through all of the people involved, all of the devices involved, all of the servers and components involved in making something happen. Not just what config do I need to like bang out the question mark on my terminal until it runs. Like, I don't know. I was never a great network engineer, but like whenever I configure BGP, I'm always just like, it's almost like infinite monkeys with infinite keyboards configuring things, right? Everybody's got a million ways of doing it. So, it forces us to actually think outside of that config box. And that makes the config consistent, right? So maybe for something simple, it's not that bad to have infinite Chris monkeys at a keyboard typing. But when you get to really complicated services like layer 3 VPNs and layer 2 VPN meshes, it gets really tough to keep that all in your mental map. So offloading that to computers, which are really good at keeping track of that, is great. That ultimately reduces the chance for human error, which ultimately makes the network more reliable. And like I mentioned, ultimately allows your engineers to stop break and fixing, stop firefighting, and just automate. Do more things. Design new network things. I really liked what Carl said. Somebody asked, how do you automate when you're trying to keep the lights on? Well, if the lights are automated, you don't have to work to keep them on. That's the goal. We're trying to make it so that our engineers are not tied up in the busy work. So, what we actually have, this is just kind of a big octopus of things. It's more than an octopus, there's more than 8, but I'm not that good with Latin roots, so I couldn't tell you how many should be. But as you can see, the orchestrator is at the center, right? So you have a user there who's going into the orchestrator, and it's talking to all these other systems. We have this thing called ESDB, which I'll show off. We have a prefix manager tool, right, which maybe goes and talks to IRR data, peering DB, et cetera, and gives us some prefix lists of what we can accept from a peer. We have network state. We have services that discover what's going on in the network. There's a lot of things. We have IP address managers, Git, et cetera. The orchestrator is the tool that is managing all of the references to those systems. At the bottom, you can see we have NSO and Ansible Tower. I should probably update that to AAP now. That's what we're using, but it's a little old. What we're doing is we're taking data from those systems, pushing data to those systems, all in one workflow, and then ultimately we're making that happen on the network using NSO just to basically configure, to translate this service structure into actual config on the devices. And Ansible can be used to deploy things to systems. So maybe make sure that a server booted up properly, Pixie grabbed the right image, and now you can SSH in and install whatever software you need, right? So the orchestrator can talk to anything southbound we want it to. So a workflow basically takes the finite resources from all those systems out there on the side, and it has all the steps you need to do that, just like a Lego kit, right? You've got all of these finite resources. The workflow has all the steps you need to assemble them in order, and then you have the final product that's been assembled. The beauty of it is, and I loved the question asked at the end of the panel earlier, which was, at the end, we take all those bits apart and put them back for use, right? We've taken the items off the shelf, we've used them, and when we're done, we put them back where we found them if they're reusable. So for an engineer, the actual workflow is going to look something like this. Maybe you're going to get a task from ServiceNow that says, hey, I need some new internet set in my place. So you take that, you're going to plan it in this tool we have called the SDB, and you're going to go into the orchestrator and say, make it so, and actually instantiate that service. At the same time, you're going to have some of the network planners designing the network and things that we want to offer, right? And actually importing the capabilities of physical network devices into our ESDB. Think of ESDB as like NetBox, basically. The only reason it's not NetBox is because it was made before NetBox, so we didn't have it to install. And then ultimately, the orchestrator is taking all that, pushing it out to support systems, and NSO could be Ansible, could be whatever you want, could be ClickSon, really whatever you wanted. And then ultimately that goes into the network and servers and things like that as network config. All right, demo time. GOAT. So this is the topology of the demo environment that we're going to go through today. So this is all running on Container Lab and using Docker and all sorts of fun stuff. It's an environment, a testing environment we built called Rover, which stands for Realistic Orchestration Validation Environment for Networks with a capital R, because acronyms are fun. Backronyms are fun, I guess. And essentially it has these 5 routers in the pentagram, which we will sacrifice things in. We have each location. The circles are the routers. The squares are like, an access switch for low speed, like 10 gig customers or something like that. And then we have some hosts and things like that. But just for the sake of time, we're going to focus only on a backbone link between 2 points on the pentagram. And it would be circuit Z00001. Because it's a test environment, we get the first circuit. And yeah, basically we also have all of these service containers which are running the software that we write and or install commercially. We have a mixture of open source and off-the-shelf stuff. So all this is running in a nice little sandbox environment that we can play with. So again, we're going to focus on this link between these 2 routers. Right now, the routers are plugged into each other. Everything's wired up physically. All we need to do is actually make it happen, right? And and these are all running on Nokia SRS vSIMs, which I will also, just while I'm getting this ready, point out to the question asked earlier about, how do we get vendors to build better virtual devices? Point them to what Nokia's done with the vSIM. It is perfect. It actually requires virtual power supplies to boot up. It's that realistic. So, there are ways that it can be done, and vendors should do a better job. All right, so I'm going to kind of show you the environment here. Of course, I got logged out. Here's my routers. So here's location 1, right at the top of the pentagram we looked at. Here's location 2. All right, I'm logged in. And we got Wireshark capturing that interface between them. Also, I apologize if you've seen this demo before. I know a lot of you have, but here we go. So here we have the Orchestrator interface. Again, this is an open source collaboration between ESnet and Surf. Essentially, this is the brains of everything. You can see here we have some active subscriptions already. So these are instances of a service that we've predefined. And these 2 instances are just, we've enrolled nodes in this system so that we can do stuff to them. And that's going to put some base configuration, set up, all the bits I need to log in without a password like I just did, et cetera, and get everything just ready to go so we can put a backbone link between these 2. Now I want to show you what this backbone link looks like in our source of truth. So in this test environment, we have, and I'm on the wrong instance here, I just noticed. Let me go to number 7. Yeah, the password is ESDB. Don't worry, you can't access it. So we'll go to circuit 1 here, and this is basically modeled. An engineer has gone in here and modeled just what the connection looks like. Now, we can do all sorts of cool stuff. We can actually nest all of the physical portions of the circuit in here, all the way down to patch panels and jumpers and things like that. But for this, we just made a logical circuit for the test environment. And what this does, because this is a nice relational database that has all the inventory of what's available to be used, we know that this circuit is connected from endpoint A, location 1, CR6, 11C21, to location 2, CR6, 11C11. And because it's a nice relational database, we can then link out, and we can go look at that device interface, and we can see if there was other circuits here, et cetera, et cetera. These are 100 gig interfaces for now, which is fine. Going over to the network device, I'm trying to move this. You can see that I'm not lying to you. And if I do show router interface, we just have the system, which is like Nokia's loopback. So we don't have any logical interface. If we do show port, 11C21 is just not up right now, and it's just sitting there ready to rock. So now that we've gone in, we've planned out our system, everything's ready to go. We go to the orchestrator, we say, I want to fire off a new process. We call it an ECMP group. I've been saying backbone link, but basically this is equal cost multipath group of backbone links between locations. So I select that, and what the orchestrator has done here is it's gone and talked to ESDB, and it's pulled a list of everything that's valid to be deployed at this point in time. So I can select Z0001. It's ready to go. We can change some runtime bits here, like maybe the IGP preference and all those fun things. And then we can submit. And this fires off a process in the workflow engine, and it basically starts populating this Pydantic data model that is used in the underneath of everything. And it talks to external systems, like our IP address manager, which is ancient and horrible, but you can actually see it's gone. It's reserved an IP block. If I refresh the page, there we go. We've got a new block here. Location 1, CR6, location 2. We got reverse DNS records, all that good stuff. But what it's done now is it's waiting for me, the engineer, to go, are we good? We ready? Let's make it happen. So as a dutiful engineer, I read this very, very thoroughly and say, yeah, that looks like it's what I want to do. And this is just the dry run. I can kind of go into, we've configured some ports. We've configured ISIS. We've configured IP addresses on here. You can see the v6, v4 addresses. But yep, as an engineer, I'm like, yeah, that looks good to me. Again, I go over here. Nothing's been sent to the device. On Wireshark, nothing is actually going across the wire at the moment. But the second I submit this, it's going to send it to our provisioning engine, which is NSO. And it's going to make the spice flow. And look at that. LLDP, ARP, ISIS, ICMP-v6, all that good stuff, BFD. It's all going. Show router interface. Look at that. We've got IPs, and everything's done, ready to go. And now I've tracked that circuit in this system. And I've even gone out and I've updated this external system here, ESDB, and I've added an orchestrator ID. And ESDB says, hey, you can't modify this anymore. It's under orchestration. It's locked it out so somebody can't go and change stuff out from underneath us. And then back to the whole topic of lifecycle, we can go in here and say, hey, maybe I want to change the state of this from in maintenance, which is what we put it in by default, to production and change the ISIS metrics and things like that. Or I can terminate it and make all of these resources here available to be used. And, it works. Let me show you. Well, I didn't test this. Maybe it won't work, but we'll see. But I'll terminate it, and, everything's going to be cleaned up. The, key's going to be left under the mat. Airbnb cleaning fee was paid. There we go. So now we just have our loop back. We're back to the way we were. So anyway, that's a quick demo of the way we do things. It's not the only way to do things, but it is a way to do things. And if you have any questions about it, we've got about 7 minutes here. More than happy to answer them. And also afterwards, if you are like, ooh, cool, I want that, or no, this sucks, come talk to me. More than happy to talk about it. All right, go for it.
Hi, this is Alex again. So I was looking at the sequence of the steps that you were demonstrating, and I was trying to see the step that would test the change before it goes live. And I saw the manual verification by a person of the configuration. So, it's got to be something more. Tell us more about, at what stage you actually making sure that this workflow works properly?
Yeah, that's a great question. The actual assurance side of thing. Right now, we don't do a ton of that, but there's nothing stopping us other than time and resources. There's nothing stopping me from, at this point, adding a step at the end of the workflow that goes and says, hey, can you ping across that? Or is it green and monitoring now? You could do all of that. There's nothing stopping you from doing it. The whole orchestrator construct that we use is very flexible. It just lets you run Python as a task or as a step in a list of steps. So if you can imagine code to do it, you can do it.
But what was stopping you to do that before? Is it just? I understand the time constraint is the biggest problem we all have. Is it the time constraint, or are there some other, constraints that you have that does not allow you to actually fully automate that in a true CI/CD fashion?
Yeah, I think one of the big things right now is, we're trying to work to bring this to more than just backbone links, right? So I showed you the backbone link, but we also do, peering with BGP and things like that. But we have a lot of services we offer, and, like with anything, you have to start small and just keep building more things. So we add on to it all the time and, just keep building stuff. Because I think if you start, every workflow has to be perfect and has to do everything and has to test everything right out the gate, you'll spend a lot of time writing something that doesn't ultimately get used, right? So we just have to choose our battles and triage because we have constrained resources like anybody else does.
Yeah, yes. Thank you.
Yeah, of course. Thanks for the question. Over here.
Hey, my name is Vishal. I'm a student at CA Boulder. I was just curious how you guys were pulling the data from the routers into your orchestrator. Like, in this scenario, you guys were using the Nokia RSL Linux. Like,
Yeah, so we're using Nokia SRS, and we don't typically pull things from the routers into our other systems too much. I kind of like the term that works in my head of documentation-driven deployment. So the idea being you document something and then it happens. Like was mentioned in the last talk, nobody goes to the AWS console and says, is that actually what we've deployed? No, because that's where you go to document it and deploy it. So the second that you document something the old way, it's going to be out of date. But if your deployments happen out of this, documentation concept of documenting your service and what it does, it's always going to be up to date. So we don't really pull stuff from the devices. Now, we do use Nokia SROS for our main IP routing core. And that is capable of, being talked to via netconf. We use NSO to basically be an intermediary. That way, we construct vendor-agnostic models in our own language of a concept like a port, and then we translate that into config for Nokia or Juniper. So this backbone link thing actually works between a Juniper and a Nokia, but the orchestrator layer doesn't need to know what the vendor is underneath, and so we're doing those kind of translations. So, yeah.
Thank you so much.
Yeah. Over here.
Hey, Chris, Tony E.
Hey.
So I've seen a couple of times today, where I've loved your demo. I've heard a bunch of times today. Looks like a very mature process that you guys are using at your organization. I've heard a lot about deployment. But what about reactionary automation, right? When something goes wrong, are you guys leveraging any kind of automation? And would you use this same platform to do that, or would you rely on something else to do reactionary?
Yeah, it's a great question. For closed loop stuff, right now we have a lot of humans in the loop, right? Because as a traditional service provider network, you got a NOC that's staffed with humans there. And so they're using this tool to react to outages and things like that. But, as you get into more AI and ML things, which we actually have some folks working on, some, ML detections of anomalies on networks, and then, using APIs to then make changes on the network in reaction to that. This orchestrator has an API that can be touched by any other system, if you're authenticated, of course. And having this orchestration layer and having all of your things orchestrated first, that's the base layer. That's the plumbing that has to happen before you can start adding stuff on top of it. So you kind of have to eat a lot of vegetables to build this. But once you do, you now have the ability to start really piling on some fancy desserts and things like that. And not that those things aren't critical. It's just that without building this foundational layer first of being able to talk to devices and have orchestrated configuration of your services, you can't then do the reactive stuff as easily.
Hi, Urs Baumann. Just a simple question. If I understood correctly, you developed everything in-house and then you open sourced, right? What was the reason? Why did you not use an existing open source orchestrator?
Yeah, that's a great question. So ESDB is not open source. That is something we developed, just as our own kind of reference database for what the network should look like, very much like NetBox or Autobot. It was developed kind of around the same time. It's the same technology stack, Django, DRF, React, etc. The orchestrator was developed initially by SURF, a research and education network from the Netherlands. They started developing it because they weren't basically happy with other tools out there that did it, so they wanted to make something that basically had this really tightly typed data model that you could get with Pydantic, which I think is very powerful. Then we came on as basically the second users and worked with them to open source it. So we didn't develop it initially. We do contribute, of course, to it as an open source project, as can you if you want to use it. And yeah, basically the idea was we wanted to build something that can be used by other people, and we didn't want to just keep it inside. And I will say, as we've made it more and more open, that's really forced our software development process to be much more mature. Because it's easy to write things for one organization, it's really hard to write something for multiple organizations. So, looks like we're time for one more.
All right, thanks. Hi, I'm Jacob Young. I like your plug about your open source project. I'll be looking into it. That's a neat piece to have for our stack too. I think it's a great idea. My question was about how do you orchestrate, servers, networking, all of that together? Does the same workflow manager do that, or do you use other products?
Yeah. So you could even think of this as like a hierarchical, I can never say the word, but a hierarchical controller of orchestrators, right? Cisco will sell you HCO that does that, but we don't have that. So this will talk to other systems. So the idea is if it has an API, we can talk to it. So for us, this is kind of the top level meta amalgamation of all of those systems. So you could think of, the AWS console or the GCP console perhaps as an orchestrator, which it definitely is. Kubernetes has orchestration bits in it. But this is sitting on top of that to coordinate all of those systems together, regardless of what they are. And just kind of one of the side effects of a really generic system like that is that it's very generic and it'll let you do everything. It's not very opinionated about, what systems you can talk to. It's opinionated about how you should talk to them, but really the idea is this is just a place where you can have a GUI. You don't have to use the GUI. The GUI is just there. There's actually a new version of the GUI that's coming out that is like individualized React components you can put into your own applications for like self-service stuff, but that's beside the point. The idea is that it's a very, it's just a task running framework to talk to other APIs. And I like that the term ETL has been thrown around a lot today because I do think we end up doing a lot of that in here, right? Just extracting data from one system, transforming it, loading into other systems. So, cool. Well, I think I've probably overshot my time, so sorry about that. Thanks.